It's my pleasure. Nigel Brandon is a dean of the Faculty of Engineering of the Imperial College in London, and his research is focused on electrochemical devices for low carbon energy applications, with a particular focus on fuel cells, electrolyzers, and batteries. He was director of the UK Hydrogen and Fuel Cell Hub. The name is SuperGen, and he's chair of the Imperial's Sustainable Gas Institute, and since 2001, he's a member of the FAPESP São Paulo chair, is excellent chair. He's a founder of the Ceres Power, which is a company that I was talking about, is focused on solid oxide fuel cells and using stainless steel supported electrolyte. And he's the chairman of the RFC Power, which is a flow battery company. Please, Professor Nigel Brandon, it's my pleasure to give you the word to you.
Yeah, thank you very much. So I'm particularly impressed, for those in the room, that you've laid on some rain to welcome those of us coming from the UK. Feels like home. So we're talking and shouting over the sound of the rain pouring down outside. So thanks for the kind introduction. I want to spend, I guess, perhaps 45, 50 minutes trying to run through a fairly broad overview of my personal perspective on why electrochemical technologies matter. I've had a really interesting short trip around your research facilities this morning and can see, in terms of looking at the labs, how much work you're doing on this space around fuel cells and electrolyzers. So hopefully you are already convinced that those who are here that this is a good idea, but I'll try and explain why I think it's particularly pertinent and particularly important for the future. I thought, given that this is going out to a broader audience, I might just start by talking a little bit about what an electrochemical technology is and some of the things that matter if you're going to try and make a technology work as opposed to a material. A material is a key enabler, but not sufficient. So we'll talk about that. I'm going to do it in the context of fuel cells, but the generic things I shall be referring to are relevant to any device that you want to make and put into a practical application that's rooted in electrochemical principles. I'm going to spend a little bit of time talking about why electrochemical technologies matter. I'm going to do it in the context of the UK energy system. So for those who are not in the UK, you will need to translate that into relevance to your own energy system. And of course, every country is different, and Brazil is particularly unique in its availability of biofuels. That's not a resource so widely available elsewhere in the world. So every country has its different challenges. If I'm giving this talk in Asia, for example, in Japan or Korea, where they have almost no indigenous energy resources and everything is important, it's a very different conversation to a conversation in the Middle East, or a conversation here, or a conversation in Northern Europe. So you need to translate the challenges into your own context, but I'll talk about it in the UK context because I have all the data and I'm very familiar with it. I'm going to focus on three particular types of electrochemical technology. There are, of course, other types, but I'm going to focus, to be frank, on the ones I work on, and therefore perhaps I'm better placed to refer to. So I'm not going to talk about lithium-ion batteries here, but obviously lithium-ion batteries matter a lot. Happy to take questions on it, but I'm going to focus on electrolyzers, fuel cells, and flow batteries, and in the context of green hydrogen and electrolysis, which is a particularly topic of greatly growing importance. Fuel cells for transport. Fuel cells have been, of course, around a long time, but we'll talk about where they sit. And in each case, I'm going to try and draw on some of our own work, my own work, and my colleagues' work, which are particularly tackling innovation and the development of technology based out of scientific advances. So how you go from university work, for example, to commercial work. We'll talk a little bit about fuel cells for heat and power, or in other countries, cooling and power. Energy storage for system balancing, with a particular focus on hydrogen and flow batteries. and see how we're going on time, but also the role of hydrogen in industrial decarbonisation. So there's a lot to cover, so you can tell it'll be reasonably high level. But what I hope to do is leave plenty of time for questions. So please think of some questions, and please do ask some questions at the end of my talk, or I shall be standing here wondering what to do with myself. So have that in mind, and particularly the students in the room. Every student should try and ask me a question, right? So please have that. Think about your question as we're going through. So what is an electrochemical technology? And I'm going to talk about it in the context of fuel cells. Now, a number of you here in the room work on fuel cells, so my apologies if I'm going to tell you things you already know. But we'll start with the chemistry and then try and work up to work through to the technology. And a lot of you here work on catalysis, and of course catalysis matters. I've shown here two images. The image on the right is the cartoon of a polymer electrolyte membrane fuel cell, the PEM fuel cell. I think that's the major area of focus in fuel cell terms here. And in a PEM fuel cell, or in fact all fuel cells, you have to have some key components. So all electrochemical devices are built around this kind of core electrochemical cell. So an ion conducting material, which is the electrolyte, and two electrodes which are in contact with that ion conducting electrolyte, where we have charge transfer reactions. And this is where the electrochemistry happens. So to take the PEM example with hydrogen, obviously hydrogen here is our fuel. It's coming in on what we call the anode. And there's a charge transfer reaction down here in which in a catalytically active region, the hydrogen molecule will form protons and electrons. And those electrons can be carried away through a current collector, and the protons will transport across the membrane, provided the membrane is a proton conductor. So obviously here we're using proton conducting materials. And then on the other side of the electrode, we have to put an oxidant, and most commonly that is air. But of course you can use other materials to oxidize, but most commonly air. And then this is where the protons combine with the oxygen to form water, but they also need electrons. And these electrons are going to be carried across around an external circuit, produced on the anode, go around an external circuit, be injected at the cathode. And of course, that flow of electrons is an electric current. And we get a voltage generated here because this reaction is a thermodynamically favorable reaction. Hydrogen and oxygen want to combine thermodynamically. They like to combine. If we were to put hydrogen and oxygen together without this membrane, of course, they would combust. And we would have a heat of combustion, we would have a flame, and we would burn the hydrogen to make steam. If we're burning the hydrogen, we're releasing heat, but we're certainly not able to capture the electrons that are released in that reaction. So we can't produce electricity directly. We can raise heat, and of course, we could use that to raise steam, and we could use that steam to raise electricity in a turbine. But in an electrochemical reaction, we're directly harnessing this thermodynamic driving force. It's related to the Gibbs energy of reaction. So the Gibbs energy of reaction tells us, in turn, depending on the number of electrons transferred, what the voltage is. So we get a voltage which is about 1.1, 1.2 volts if we've got hydrogen and oxygen. And then as we draw current from this reaction, the reaction proceeds around an external circuit, the voltage will go down. And of course, the voltage will go down because we have voltage losses associated with the flow of current. So we have none of these materials have an infinitely high conductivity. They have a finite conductivity. So we have a resistance of the membrane associated with its ability to conduct protons. We have a kinetic resistance associated with the electrochemical kinetics of these reactions, which are measured by things like exchange current densities and so on. We have materials that have to conduct electrons that have finite conductivities. So again, we get some resistance. So we have a resistance of the cell. So as the current goes up, the voltage goes down. And the combination of voltage and current, of course, is power. So we produce power as we pass increasing amounts of current. But the efficiency of the device depends on the voltage. Right? So the maximum efficiency of an electrochemical device, but in a fuel cell context, the theoretical efficiency is the Gibbs energy over the enthalpy of that reaction. So as we're lowering the voltage, which is directly related to the Gibbs energy, effectively you could consider it as low as lowering the Gibbs energy. So the efficiency falls as the voltage goes down. So when we start to think about how we design a fuel cell, we want to make certain that the resistance, the internal resistance, all of these resistances together are as low as possible. That's a really important thing. And we have a choice about the voltage we operate the fuel cell at. If we operate at a high voltage, we'll have a higher efficiency. If we operate at a low voltage, we'll have a lower efficiency. If we operate at a high voltage, we'll have a low power density. But if we operate at a low voltage, we'll have a high power density. So in practice, you have a choice between power density and efficiency. So this is a completely different characteristic to a heat engine, like an internal combustion engine. So a heat engine has an efficiency load curve, which is very peaky, so it's not very efficient at high load and it's not very efficient at low load. A fuel cell has a very different characteristic. It's very efficient at low load, and it's less efficient at high load, but it's still more efficient than a heat engine. So it has a different set of characteristics. And that's something that people who don't work in this area find quite hard to grasp. So if you're used to heat engines, completely different set of characteristics. So that's how all of this relates together to some of the characteristics. In a minute, we'll look at how it relates to some of the engineering challenges. A solid oxide fuel cell, which is the area I mainly work on in fuel cell terms, is a higher temperature device. Now we have a ceramic membrane that conducts ions of oxide ions. The principle is exactly the same. We're putting fuel on one side, we're putting air, oxygen from air on the other side. But now in this case, you can see protons are going across the membrane. Here, oxide ions are going across the membrane. And they're driven across the membrane because this is an oxide ion conductor at temperature. And temperature means somewhere between probably 500 and 900 degrees centigrade. So these are high temperature devices. At this reaction here, we're putting in a fuel like hydrogen, but could also be other things like carbon monoxide. And that's being oxidized with these oxide ions to form water. But at the temperatures we're running at, it forms steam. So this is an entirely gas phase reaction. In this case, you can get liquid water formed on this side, which is an engineering challenge. We again release electrons. Those electrons go around the circuit. They combine with the oxygen at the air electrode to form oxide ions. So the overall reaction is the same, but we now form our steam in the fuel stream, and in a PEM we form our water in the airstream. So there are some practical differences between the two. Okay. So I should just perhaps stress that, so this is the domain where catalysis matters a lot, where your ionic membrane materials matter a lot, where the design of the microstructure of your electrodes because you've got to get gas transport in, water transport out, or gas transport in, steam transport out. The microstructure matters a lot. This is the domain where these things are very important. So if we have a good catalyst and a good membrane and a good everything else that gives us a low internal resistance, we might want to start to think about making a stack of these things. Why a stack? Because an individual cell produces, let's say, about 0.7 volts, and perhaps it might produce, let's say, 1 watt per square centimeter. It depends on the technology. Some are a lot higher, some are lower. But if you want something that's got hundreds of kilowatts, you're clearly going to need many cells. So we have to find ways of joining cells together. There are practical limitations on the area we can make. Because obviously area, if you make the area of the cell bigger, you make the current higher, but you make the voltage the same. The other option is to make your cells, stack your cells up in electrical series, which is what this cartoon shows. So a series of cells joined together, and if you stack them in electrical series, then the voltage steps up, but the current stays the same. And actually high voltage, in practical terms, is easier to manage than high current. It's cheaper to manage voltage than current at scale. So here we have a PEM fuel cell schematic, and this looks very similar to some of the test rigs I saw when I came around and looked at the labs earlier. So this is a small scale, but it makes the point, right? So we have to have an MEA. So this is our catalyzed membrane with our electrodes on it. We have to have flow field plates that are in contact with that will distribute in the fuel in the air. They have to be sealed. And then we have to be able to stack these different devices up. We have to find a way of delivering uniform flows of fuel and uniform flows of air over that. So we're now starting to get into flow distribution. We're starting to think about thermal fluids. We're going to have to think about compression loading on this so that we've got a uniform compression force on each of these cells, so that we've got the cells are flat and in good electrical contact with each other. If they are not, then the resistances will be high. So we need to think about the mechanical engineering of this device and the thermal management of this device. Okay, and then we go up in length scale again because we've managed to make a stack that's quite good, right? It's got good materials, good catalysts. We've managed to get the engineering of the stack right. Now we have to make a system. So this is a cartoon schematic of a fuel cell engine from an automotive application. And here's the stack, right? So we've spent all this time so far worrying about the stack. But the stack is actually just a relatively small part of that component system. It's probably one of the most important parts, but it's not the only part. So not only do we have a stack, we have to have heaters, we have to have coolant pumps, because this will be a liquid-cooled device almost certainly at this power density. We have to have air filters, we have to have fans for blowing through air through the device. For feeding it, we need some inverters. Obviously, this is going off into an automotive or truck application, so it's also driving things like an air conditioner. It needs a compressor on the air side because it's a pressurized device. So we're now into systems engineering. So now we've got to get all of this working together, and we have to have an engineered system that will treat our stack, which is in here somewhere, carefully and sensitively to give us the right sort of performance and lifetime and cost. So this is a piece of electrochemical technology. And when I say electrochemical technology, this is what I mean. An integrated system that you can use as an end user who doesn't really care that it's a fuel cell. They just want something that, in this case, will produce power efficiently from a fuel and work every time they switch it on. They don't really care now, by the way, what the catalysts are. They just care what it costs and that you can make it the same each time. So, of course, in the science labs, we care a lot about this. And in applications, we care a lot about this. So you need an integrated perspective. So when I'm talking about the subsequent technologies, ultimately, this is where we need to get to with all of them, some equivalent of this. Okay, so why does it matter? So I spent a lot of my career of late, less so now, trying to persuade people that these technologies are important. Because for a long time, people haven't really felt that they were important. And why actually are now people getting interested? So this is the UK energy system. For those, just to talk it through. So this is energy in gigawatt hours per day. The UK is a small place, don't forget. So this is gigawatt hours per day. This is time by year. This is all real data. It's put together by a colleague who does really nice work in this area at the University of Birmingham, Grant Wilson's team. And this is the flow of electricity through the UK energy system, which is this squiggly line at the bottom. You probably can't read that number there, but in 2022, the UK's electricity was 39% gas and everything else, and 1.5% coal, but everything else was low carbon. So we've made actually good progress in decarbonizing this, but you can see that sadly, it's the least important part of our energy system in terms of the amount of energy flow. But it's probably the most important part of our system in terms of the potential for decarbonization. So that's electricity. You see some seasonal variation. So this is our winter, right? And this is our summer. So there's a little bit of a shift between summer and winter. This is the flow of energy as liquid fuels, which is essentially all gasoline and diesel. This is the COVID impact on transport consumption, energy consumption, and it's still not quite picked up. So that is essentially all fossil. And of course, one of the things we're interested in is whether we can use electricity to decarbonize fossil by having electric vehicles. And just to give a sense of scale, right? So an electric vehicle is a lot more efficient than a gasoline vehicle. So this is about 1,600 gigawatt hours of energy to go through to deliver our transport fleet in the UK. If you've got roughly 3 or 4 times the efficiency in an electric vehicle, let's say it's 4 times, let's be generous. So that's somewhere in the region of another 400 gigawatt hours of electricity we need to produce. bearing in mind at the moment we're at about, on average, somewhere like 800 gigawatt hours. So to replace all of this with electricity, you need to generate roughly twice as much, half as much electricity again. Okay, that's the sort of ballpark number. Secondly then, what's this big flow here? So this is the flow of energy as natural gas. So we are a very natural gas dependent economy. That's because the UK has North Sea gas. We've been energy independent of North Sea gas since the 70s. And other parts of Europe, of course, are very dependent on natural gas. And you'll be more than aware, if you followed the issues with Russia, what the chaos that's causing in Northern Europe. So we are very sensitive to, and this is primarily for heat. Not entirely, because we use, obviously, some of it, gas, to make electricity. But you can see that there's big seasonal variation, and this is our winter, and this is our summer. And in the winter, we have a lot of gas heating because it's cold. So that's a big challenge. Those seasonal variations are enormous. And if you wanted to replace all of this gas heating with electrical heating, because you're going to decarbonize the electricity, this is about 4,000 gigawatt hours peak. And so you would use a heat pump, which gives you about 3 to 4 units of heat per unit of electricity. 4 if you're really lucky. So let's say it's 4. That's 1,000 gigawatt hours of power. So this is 1,000 gigawatt hours. So this peak, this would go up like this, right? So you're going to have to put in an awful lot of generating capacity with a very seasonal variation, which means in the summer you're not using that sunk investment. So it's a really expensive thing to do. But that's the context in which we're looking at decarbonization. So why do electrochemistry matter? Well, electrochemistry technology, we saw with fuel cells, is all about moving between electrons and molecules, right? And this is all about how do we move between electrons and molecules, whether those are molecules for heat or molecules for fuel. And of course, some of that can be direct use of electrons. And so if we can use electricity directly, we always should. No brainer, right? If you can use electricity, use electricity. But if you can't use electricity, and we'll look at some applications in a bit where it's much more difficult to use electricity, like flying an airplane with 300 people on it across the Atlantic, you need a fuel. And so if we need a fuel from electricity, and given that electricity is increasingly going to be the input stream for, in addition to biomass, and of course the biomass conversation here is probably the most important conversation. In most countries it is not. Is that electricity and biomass are going to be two very important energy input streams to the low carbon system of the future. So how do we convert between those into things we need to perform transport and heat or cooling is very important. And equally, how do we go from molecules to electrons is very important. So electrochemical tech sits at the heart of all of this. Now, the other reason people are interested in this is because of air quality. It's a huge driver in Northern Europe. It's a huge driver in the UK. This is London. It's a little bit old, but it's only got worse, I think. And it's a NOx map of London. So for any of you that have traveled to London, this is Heathrow. I live about here somewhere. And Imperial College is in about here. And the higher the red line, the higher the NOx level. And the red NOx levels break all European rules on air quality. So, and these are coming entirely from transport, right? So these are all transport-related NOx emissions off internal combustion engines. And so trying to move away from internal combustion engines is not only about carbon, it's also about air quality. And there's huge sort of increasing amounts of policy intervention going into driving these changes. Okay, so one of the things when you talk about electrochemical tech is the topic of hydrogen. So hydrogen is potentially a low carbon fuel, a low carbon energy carrier. I'm going to talk more about it. And of course, we make hydrogen commercially today. We make it at a large scale. The world makes about 100 million tons or so of hydrogen a year, 98% of it made from natural gas or coal. All of it effectively for either making ammonia as a fertilizer or chemical feedstocks like methanol or refining petrochemicals. It does not make hydrogen as an energy carrier, it makes it as a chemical feedstock. But if we're going to want low carbon molecules in here, as well as our natural gas or our fossil fuels, the next easiest low carbon molecule to make is hydrogen from splitting water by electrochemistry. It's the electrochemistry I'm going to focus on, but you can make it other ways as well. So this is a color map of all the different routes to hydrogen. I have to say, I don't think, given the conversations here in Brazil, that there's a color for ethanol-derived hydrogen. So we need to think about a color for ethanol. Or someone has, it's just not on this picture. So what's the color of hydrogen if it's made from ethanol? I have no idea. Because strictly green hydrogen is made from renewable power, but it could equally be made from ethanol. Anyway, interesting question. So there are many different colors of hydrogen. The two most commonly people refer to in the context of low carbon hydrogen are green, which is largely by electrolysis, or blue, which is largely from natural gas with carbon capture and storage. So this is zero carbon, arguably. We'll look at that in a moment, and this is low carbon. But you can make it by all sorts of other different routes, and there are lots of different colors, but those are the main two. So once we start to thinking about hydrogen as an energy carrier, or indeed any fuel as an energy carrier, we have to think about its carbon intensity. And why is that? Because hydrogen really, other than in very unusual circumstances, does not exist naturally. You have to, it's in the form of water, it's in the form of methane, it's in the form of hydrocarbons, and you have to put energy in to separate the hydrogen from its carrier, right? You have to put energy in to make hydrogen from water, for example. So this is some work of an organization trying to create a green hydrogen standard. I just think it's an interesting example for us all to have in mind. So they've defined a green hydrogen standard of 1 kilogram of CO2 equivalent per kilogram of hydrogen, bearing in mind that today it's around 10 kilograms of CO2 per kilogram of hydrogen if you make it from natural gas. So today's hydrogen from natural gas is about 10. And so this is 1. So that's the target. But then you have to start to think about, well, what are we including in that, right? So this is suggesting all of the energy input streams should go in, and all of the implications of the production processes should go in. But it doesn't include upstream emissions, and it doesn't include downstream emissions. But in practice, of course, from a societal perspective, we need to think about upstream emissions and downstream emissions, as well as the energy inputs, as well as the processes. So when we talk about something being zero carbon, it's never actually zero carbon, because there's so many other input streams that are going in. But it's important, particularly as scientists and engineers, that we're very open and aware of these, if you like, energy and mass balances when we're starting to think about challenges around sustainability. So that's why I think this is quite a helpful slide. And this is a paper we wrote some years ago about the role of hydrogen in the economy tomorrow. So if you go back to the 60s, John Bockris gave a talk at General Motors where he spoke about the hydrogen economy, and there was lots of sort of excitement in everything being powered by hydrogen, and you wouldn't need any other form of energy carrier. The reality is that will never happen. That is not what it's going to be, but that we will see increasing amounts of low carbon molecules, hydrogen or its carriers like ethanol or methanol or ammonia, in the energy system in support of electrification. And it's this partnership between electrification, because if you can electrify, that's what you should do, and low carbon molecules where you can't electrify because it's not cost effective or functionally possible, or the electricity is being made where you don't need it, for example, in the middle of a desert, when you need to start to think about making molecules. So this is a cartoon of the role of hydrogen in the economy rather than the hydrogen economy. Okay. Just talk a little bit more about this before I go back onto my electrochemistry. I gave this slide when I was here in September. I thought it's worthwhile rephrasing it, or not here, but at the Sao Paulo campus in Sao Paulo City. And this is about the costs of grey and blue hydrogen. So this is hydrogen from natural gas. And obviously it makes sense that if you're making hydrogen from natural gas, it will cost more per unit energy than the natural gas, right? It's got to, because you've done stuff. separated out CO2, stored CO2. This all costs money. Historic gas prices in Europe, 20 euros per megawatt hour. We'll talk about where gas prices are today in a moment. And obviously the price of the hydrogen goes up as the gas price goes up, okay? About 2 euros per kilogram at 20 euros per megawatt hour. This is the natural gas prices in Europe. When I last came to Sao Paulo, it was September last year, and we were about the peak of over 250 euros per megawatt hour relative to the historic of 20. So we had over 10 times increases in gas prices in Europe. If you look at the energy dependence in the winter in Northern Europe and the amount of gas we use, you can see the pain point that hit everybody in Northern Europe this winter. We didn't run out of gas, but it's been a very expensive winter. In the UK, which is a relatively wealthy economy, the government have provided direct subsidy to everyone to help them meet the cost of their energy bills this winter. So it's been a big deal. So obviously, hydrogen made from natural gas is very sensitive to the natural gas price, and you can see the consequence of a war in Ukraine, which is exactly what that is a consequence of. The gas prices relaxed back to about 50 euros per megawatt hour relative to the historic norm of 20. So we're about 2.5 times the price, but we're not into these amazing areas. But what it has done is it's led to things like this in the European Union, right? Really bold, ambitious targets to move away from natural gas. So this isn't about carbon, this is about resilience, it's about energy security and the ability to be independent of imported fossil fuels from countries you don't like. And so that is a huge driver at the moment around hydrogen and its carriers that in a European context is worthy of note for those of you who are interested in Europe as a market for your energy products. What about green hydrogen? Well, green hydrogen is made from electricity, so it's primarily sensitive to the electricity price. 60 to 80% of the price of green hydrogen is the cost of the electricity that goes in to make it today. So this is some sensitivity to power price. If you're looking at sort of historic power prices, you can see we're about 4 euros per kilogram for green hydrogen. And that's why when you read things, people say, well, look, green hydrogen is great, but it's a lot more expensive than blue hydrogen. Well, that's true, except when the gas price goes up to 50, you're now at 4 euros per kilogram, which is where you are with green today. Now, the green hydrogen price, therefore, is going to be heavily advantaged in countries with low-cost renewable power. And that's one of the reasons you're seeing the Middle East and Australia make huge investments and bets on green hydrogen. You'll see the same in Southern Europe, in Spain, in Portugal, where they have very low-cost advantaged renewables. So there are some really interesting geopolitical questions around who's going to be producing this in the future and where it will be produced and how you move it around the world and so on. Okay, so there we go. Let's dive into some technology stuff. Okay, so I'm not going to spend a lot of time on these, but just to give some flavor, right? So alkaline electrolysis, we're going to talk about electrolysis. So electricity in, hydrogen out, water splitting. Alkaline electrolyzer has been around for 100 years, very mature. You can buy a 100 megawatt system and go and put it in a desert in Saudi, which people are. So it's a mature technology. It relies on this kind of potassium hydroxide, porous diaphragm soaked electrolyte membrane. Because it's porous, one of the challenges with this technology, you can't make hydrogen at pressure very easily because you can't manage the pressure drop across this porous membrane. It's about 65% efficient. This is a kind of flow sheet, lots of balance of plant, takes up a lot of room, but it's the cheapest form of technology today and available at scale. PEM electrolysis, relatively new, comes effectively quite substantively derived from PEM fuel cells, but not the same. Again, has these proton conducting membranes, has to have catalysts in it. These electrodes are catalyzed. These catalysts at the moment are quite expensive materials and they're quite rare materials. And I know that people here and elsewhere around the world, of course, are working to find replacements. So platinum on the hydrogen side, iridium and ruthenium on the oxygen side. Iridium is the rarest metal in the world. So, you know, there is a concern about cost and there is a concern about material security. The advantage of PEM electrolyzers, however, is they do produce hydrogen at pressure, which is a big up if you want to put it into for example, vehicle refueling. They're also about 65% efficient at the moment, but they're much more compact. They have less balance of plant. You can fit them into a much smaller space. And then the technology I work on, I'm very interested in, which is high temperature electrolysis. So we're now talking about the electrolysis of steam. This is not a mature technology. You can't go and buy one. But the motivation here is all around the thermodynamics. So if we look at temperature, the Gibbs energy, and if you remember earlier, I said that the Gibbs energy is related to the voltage you produce from a fuel cell. It's also there for the voltage you need to put into an electrolyzer. So as the temperature goes up, the Gibbs energy goes down, which means you need less electrical work to split water compensated with heat. Still need the same amount of energy because the enthalpy hasn't changed very much. So in a high temperature system, you put in less electricity and some heat. And heat is much cheaper than electricity. And if you've got the right industrial very high efficiency electrolysis, much more efficient than at low temperature. This is a paper from a German group, which I quite like to reference, and it paints a picture of these different technologies. So this is alkaline electrolyzers, conventional alkaline electrolyzers. There's a whole field of alkaline membrane electrolyzers, which is very interesting, but they're not on here. PEM electrolyzers and solid oxide electrolyzers. This is efficiency. This is current density. So current density, higher current density, smaller bits of equipment should be cheaper. Efficiency obviously lowers your power consumption. That matters because 60 to 80% of the cost is the cost of the power. So if you can be more efficient, that makes a big difference. So the reason we're interested in high temperature electrolysis is we can get north of 90% efficiencies, already demonstrated by people like Sunfire in practical systems, close to 90%. In principle, now we have to be careful here with our thermodynamics, you can get over 100% efficiency. And of course, you can never get over 100% efficiency. It doesn't make sense. So this is effectively it's correct, but it doesn't allow for the heat. So to be over 100, we've effectively got an endothermic water splitting reaction in which we're injecting additional heat to balance that endotherm, and that gives you an apparent electrical efficiency of over 100%. Total efficiency, of course, can't be over 100%, but you can recuperate heat effectively to displace power. So you get, but even without those tricks, you get very high efficiency, right? So it just paints you a map of the different technologies and their pros and cons. So I'm going to talk a bit about solid oxide electrolysis because it's the area I work on. And I know it's also an area of interest in general here, with some work going on solid oxide in Brazil and at USP. And you've got three broad types of technology when you talk about solid oxide. So these are the ceramic devices, right, to remind us. So in all of these cases, you have an electrolyte, which is this brittle ceramic material. It's an oxide ion conductor. So when we're trying to think about solid oxide devices, we have to be really thoughtful about what our electrolyte is, and there aren't that many choices. And because it's a ceramic, it's brittle. So they don't bend. They don't take strain very well, they crack. So we have to think about how we engineer this ceramic to be mechanically supported. And there are three approaches to this. The most common one is to use what's called the fuel electrode, the anode in a fuel cell term, it'd be the cathode in an electrolyzer, but this electrode that's on the hydrogen side is the mechanical support. It's a porous mixture of metal, usually nickel, and the electrolyte. And then a thin, like 10 micron thick, electrolyte, and then an air electrode. That's called an anode supported cell, and that's probably the one that most people are developing around the world. Then you go to an electrolyte supported design. So in an electrolyte supported design, here the electrolyte's about 10 microns thick, here the electrolyte's about 150 microns thick. Human hair is about 100 microns thick. But at 150 microns, it's strong enough to support its own weight. This is the type of technology that Bloom use in their solid oxide fuel cell, for anyone who follows that. This is a fuel cell energy type technology. And that's okay, but of course, at 10 times the thickness, it's got 10 times the resistance. And you've got a lot of relatively expensive material. And then the type of cell that Ceres pioneered is this one, which is the metal support. So now your mechanical support is some stainless steel, some ferritic steel. And then you have a thin anode and a thin electrolyte and a cathode. And of course, this gives you much better mechanical integrity, and it's cheap and low cost. But the question is, how do you have a material set that's compatible? So that's the broad space. And if you look at a cross section through, this is just a sort of generic cell with an electrolyte supported cell. So this is your sort of 120 or so microns electrolyte. Your air electrode, which tends to have a couple of different microstructures, high surface area where you want the catalysis, coarser where you want the current collection, and a fuel electrode, which again has high surface area where you want the catalysis, it's coarser where you want the current collection. So we were working on this at Imperial in the late 90s. And we had a grant from our research councils to develop this concept of this intermediate temperature solid oxide fuel cell. And we patented the cell design, and this is the cell design, which is essentially still what's made. You'll see a more sophisticated version in a minute, which is a porous steel with these layers on it. And that was the core patent that we then transferred to create a business, which we called Ceres Power. We called it Ceres because it uses doped ceria in the electrolyte, and therefore that's where the Ceres name comes from, who's also the Roman goddess of grain and life. So some simple geometries, and that's the core patent, and we created a business off that, and we went off and raised money. So that's the business that's now worth about 350 million pounds. Sadly, I own almost none of it by now. But this is what the cell structure now looks like. This is a cartoon of what the cell structure looks like. And this is a photograph of a Ceres cell. So you can see that compared to the patent, I mean, these are the key features. These are the fuel and air plenums and so on. It's evolved, but it's not evolved beyond the patent. So now we have, this is showing you the electrolyte, the anode, which is this gray layer. And then there's a completely transparent electrolyte that you might just be able to see lapping over on the edges that seals it in place. There would then be an air electrode on this, which is a black layer. And you can see that the support material has made with a bit more sophistication in terms of the sealing arrangements and the flow distribution arrangements. A porous ferritic steel substrate, a ceria nickel cermet as the anode, a gadolinium doped ceria. Importantly, for anyone interested in using gadolinium doped ceria, it's a difficult electrolyte material to use. It becomes mixed conducting in fuel environments, even at 600 C. So they put a blocking layer of an unspecified electron blocking layer on there, which blocks any mixed conductivity, without which you can't really get a high efficiency device. And then a cathode, and they don't tell you what the cathode is. So, but it's a perovskite. So that's the material set. The key advantage of all of this is that you can have a welded seal and a gasket seal. So almost the entire motivation for all of this effort is you can have a high integrity seal. You don't have to have a glass ceramic seal, and all of the other devices have glass ceramic seals, and they're a complete nightmare to engineer a robust and reliable device with. So you can have all the best chemistry in here, but if the seals don't work, the stack breaks. And what you find with most technology is you thermally cycle it up and down in temperature, the seal fails. The big advantage that Ceres have is that the seal doesn't fail. And that's one of its principal characteristics. Of course, you've got to get all of this right as well. So where are they today? You can look them up on the internet. This is public information. So they have partnerships with these companies. You can now buy a CHP product in Japan. Bosch are building a factory in Germany. They're looking at marine applications with Doosan. They're putting them on buses in China. And most recently and relevant to the electrolyzer story is that they're developing an electrolyzer variant of this as well, and that this is public knowledge that they're putting a 1 megawatt machine into India in partnership with Shell at the moment. And in terms of what we do in my group, in our research, we remain very interested in some of the fundamentals and how you continue to evolve the materials. So we're doing things like electrospinning to produce interesting fiber structures, which we think are much more robust, particularly focusing on electrolysis mode, where you can have problems with nickel migration at the high steam concentration. So we're interested in developing novel fibrous structures for these applications, which we continue to work on today. The other area we're working on is on the modeling and simulation side, where we do a lot of work, mostly for us. Well, we don't really work down at this level. We're at the continuum level. So we go from microstructure to system in terms of our simulation work. But if anyone's interested, they can let me know. Okay, conscious of time, I shall march through some pictures on transport. So this is our Toyota Mirai, which we've had at Imperial. Toyota have recently taken it back. I understand that USP are going to get one of the new Toyota Mirais, which I look forward to seeing. I don't know if we're getting one, but you're getting one. But I have to say, light-duty transport is not the cutting edge of hydrogen for transport at the moment. I think battery electric is the cutting edge. Let's see where hydrogen gets to and fuel cells for transport for light-duty. But batteries are a tough competitor. But I do think as the vehicle size goes up and the amount of energy you need to carry on the vehicle goes up, then hydrogen fuel cell, or fuel cells in general, become a really attractive solution for electrification. Buses, particularly public buses in Europe, noting the issues around air quality, are of growing interest. Hard to do with electric, definitely possible with hydrogen fuel cell. Trains, a big deal in Northern Europe again. So we have obviously got electric lines, but we have lots of lines that are not electrified. They're diesel electric trains. They're too expensive to electrify. They don't carry enough passengers to warrant the cost of electrification. By going with a hydrogen fuel cell solution, you create an electric train option that avoids the cost of electrification. So that's something that's really growing of interest in Europe, particularly been driven in Austria and Germany, but we have some on trial in the UK as well. Trucks, so heavy-duty vehicles which need high amounts of energy. Again, there are companies seeking to electrify trucks with batteries, but there's an equally fierce competition going on about electrifying trucks with fuel cells. So that's, and indeed there are companies looking at hydrogen combustion trucks, not electrochemical tech, produces lots of NOx. I don't know if it's the right answer, but obviously it's an area people are looking at. So heavy duty vehicles are really interesting space. And then maritime. So I was in Singapore a few weeks ago, huge interest in how you decarbonize shipping. And that has to be done with a low carbon fuel. You can't do it with batteries beyond some small inshore craft. And what is the future of shipping fuel? Whether it's hydrogen or ammonia or methanol, should also consider ethanol, but no one is at the moment. You know, a really important space. Someone gave me the statistic, and it was Shell that gave me the statistic, so I suspect it's broadly right, which is that the 16 largest ships in the world can produce or consume the same amount of fuel as all of the world's automotive cars. So very big energy consumer. And then, of course, the toughest space of all, which is aviation. What are we going to fly around the world in? It's not going to be batteries. So it's got to be a fuel. Is this where we make synthetic fuels? Because all synthetic fuels are made from hydrogen anyway, and so on. So we're doing some work with one of these companies at the UK developing hydrogen fuel cell solutions. Where's the innovation in fuel cells? So my colleague Anthony Kusinak was here a few weeks ago. He may have spoken about his work with Bramble, which I think, it's not my work, I think it's a really interesting idea where you take printed circuit board technology and make fuel cells using it. Easy to say, hard to do, but it's a really neat idea. These are his slides. I think it's another example of how you take breakthrough ideas in a laboratory concept, which give you manufacturing advantages and take them into commercialization. And recently they've raised a very substantive amount of money to take that technology forward. So it's a really interesting approach. I have to, of course, cite the project we're working on here in Brazil with Shell as well, which is looking at solid oxide fuel cells running on bioethanol for transport applications. And that's a program we're working on, and I think it's a really interesting challenge. So that's a research project here in partnership with Shell, which we'll have a workshop on tomorrow. Outside of transport, then, fuel cells produce power and heat. So they are very useful for applications where you need power and heat. And I've shown already the challenges of natural gas in a country like the UK. This is a report we wrote through our Sustainable Gas Institute some years ago. It looks at number of households connected to the gas network. This means the natural gas network. And the UK has the second highest fraction. The highest fraction is the Netherlands, so of course the other side of the North Sea. Italy, Singapore, Australia, Belgium, and so on, right? I suspect Brazil, here's Brazil. So it's not such a big deal here, at least when we wrote this report in 2017. So how do we get away from that? Well, one of the things the Japanese are doing is to use fuel cell micro combined heat and power units. So they put a fuel cell in the home, and it produces power for the home. It supplements rooftop solar, for example, and the waste heat that the fuel cell produces. So if the fuel cell is 50% electrically efficient, say, or 60%, it's producing 40% to 50% of that energy as heat. And obviously a solid oxide fuel cell is producing that as steam. So you can use it to heat your home, you can use it to produce hot water. And so this is a kind of Japanese, and there's over 400,000 of these now installed in Japanese homes. Not running on hydrogen, running on propane and butane, but they could run on hydrogen in the future. And I should stress that you can now buy fuel cells, right? People are selling fuel cells. And if you look at the market from this fuel cell industry review, which is a very useful document that E4Tech produced, you can see that it's dominated by PEM fuel cells. This is by fuel cell type in terms of numbers of shipments. This is in terms of megawatts. And it's dominated by PEM for transport. But the next most dominant one after that is solid oxide. And these are the units, for example, for that Japanese program, which is so dominant in terms of numbers. So things are happening. This is a Bloom power unit, which you find a number of them in the US. This is the Japanese, the series Japanese product with Mura. I'm conscious of time, so I'm going to just move on swiftly. The other thing with hydrogen, which is for countries going for very high renewables, how do you provide a resilient system that doesn't rely on having natural gas backup? At the moment, we back up what renewables we have in the UK with natural gas. But if you aren't going to use natural gas, you can't do that. So this is an estimation from a colleague of mine, Goran Strabak, which says the UK will base its renewables on wind. We're a very windy place. We have lots of wind. We have the best wind resource in Europe. So, but the challenge, what happens in our area of the world, is in the winter, the wind stops blowing. And it stops blowing for several weeks. It always does every winter. So if you're reliant on that wind to produce your power, and you're going to use that power for heat, that's a bit of a challenge. And this says, well, if there's say 4 weeks with no wind, how much energy store do we need to back it up? And we need somewhere in the order of 20 to 40 terawatt hours. That would back up the UK energy system. This is we only have 2 of these in the UK. This is a pumped hydro facility. It's quite big, you can see. It's in Wales, and it's 9 gigawatt hours. So to back up 33 terawatt hours, which is what you get with 1 million tons of hydrogen, you need 3,600 of these. So to deliver this, 30 terawatt hours, we need 3,600 pumped hydro facilities. And we simply can't. They're hugely expensive to build, and we haven't got 3,600 mountains to put them in. So the interest in hydrogen, or a molecule like hydrogen, is that 1 million tons of hydrogen can provide, if you could store 1 million tons of hydrogen, you would provide the strategic reserve needed to back up our entire country's energy system for a month. And so there's been some nice work done in Germany looking at the technical potential of underground hydrogen storage. What you do is you take a salt deposit, you solution mine it with water, you create a cavern, and you put the hydrogen in there. That is not science fiction. We already have one of these in the UK. The US have lots of them. They're used as backup systems for petrochemical facilities, so it's entirely practical. But obviously you need a salt deposit. And not everywhere has a salt deposit, but they did a technical assessment of the salt deposits across Europe. And here we are in the UK. And given that we need some tens of terawatt hours, we actually have the capacity for over 1,000 terawatt hours. And many other countries in Europe do as well. So there's some interesting options for long-term strategic reserves using things like hydrogen. And then finally, the other energy storage question is as you get increasing penetration of solar, this is a California study that looks at the implication of having very high solar PV installation, which is where California will go. And this is their dispatch from solar. And what they find is that they get this big, and not surprisingly, right, they get some big, lots of solar in the daytime, and of course very little at night. So they need about a 10-hour energy store to balance this shortfall. And this is where things like flow batteries come in. So a flow battery, just in very brief terms, this is a vanadium flow battery, which is the current kind of commercial incumbent. And a vanadium flow battery has, as the name suggests, it has a liquid electrolyte comprising an acidic solution of vanadium salt. And you can change the oxidation state of vanadium. It sits in 4 oxidation states. So you can have a 2,3 couple and a 4,5 couple. So you can create the 5 oxidation state and the 2 oxidation state by charging the electrolyte up when you've got power. And then you can flow that back through the same cell, and that will work then in fuel cell mode to generate the power back. That gives you about an 80% round trip efficiency. So you get about 80% out of what you put in. But it has the big advantage that if you want more energy, you just have more electrolyte. So with a lithium-ion battery, if you want 10 times the amount of energy, you need 10 times the number of batteries. And so that costs 10 times as much. With a flow battery, you just make the tank bigger. So the cost scaling depends on the cost of the electrolyte, rather than, so it doesn't scale linearly because tanks are cheap. It depends on the cost of the electrolyte. So for long periods of storage, like 10 or more hours, but flow batteries are of interest. So again, just to pick up the narrative of going from research to commercialization, and this is work I do with Anthony Kusinak, who was here, as I said, a few weeks ago, and other colleagues, of course. Academically, we created some patents on a novel chemistry, which we've also published because it's important to sort of get peer review of what you do once you've patented it. And that we've taken out into this company, RFC Power, and that's now scaling this up. And the key is that it uses hydrogen in a closed loop on one side and manganese in solution on the other side. So it looks something like this, looks something like this. This manganese solution is a far better alternative to vanadium. It's a fraction of the price, 1/10 the price of vanadium. It's very abundant. You will find manganese in every primary battery that you have. Every little Duracell battery is full of manganese. And on the other side, we have hydrogen in a closed loop. So works like an electrolyzer or fuel cell on the hydrogen loop side. And hydrogen is a very facile reaction. It's much quicker than the vanadium equivalent, so you get high current density. The manganese is very cheap. The hydrogen can, of course, in time be coupled into a hydrogen system if there was one, so you wouldn't even need a hydrogen loop. But at the moment, we have a closed hydrogen circuit. You do have a problem with the manganese disproportionation reaction. And Anthony's group did some really excellent work to find a way to stabilize that and stop that disproportionation reaction or manage it. So that's where we are with this technology, and we believe it gives very low cost, and it's being scaled up at the moment. And then finally, and the last slide is about decarbonization of industry, which is another huge issue, which is how do you decarbonize the steel industry? For example, if we continue to make steel the way we make steel, steel alone will use up the world's entire carbon budget for a 1.5 degrees C climate scenario. Of course, we make steel using coke, so you can think about using hydrogen to replace that. But I'm going to stop at this point and just go to my summary slide. What I hope I've shown you in my whirlwind tour is that for those of you working in electrochemical technologies, this is actually a really important space. Not everything will be electrochemical, but electrochemical will be a very important part of the system of the future because of its efficiency and its flexibility and its conversion between molecules and electrons. I hope I've shown you that hydrogen and the carriers of hydrogen, like green ammonia or methanol or ethanol, big deal here, of course, it's bioethanol, will play an increasingly important role. We are still going to need carbon molecules. I think that's where the biomass comes in. And of course, there are some really important challenges which we don't currently face as we continue to put more and more renewables into our energy systems with intermittency and the need to flexibly balance supply and demand, where flexible high efficiency technologies come in. And I'd just say that international collaboration is important, so it's great to be here. Looking forward to continuing the collaboration going forward, because there's a lot of work to be done and we don't have a lot of time to do it. So with that, I'll close. Thank you very much.
Thanks, Professor Nigel, for this very interesting talk. We now open for questions. Hamilton.
So thank you very much. I have the first point is concerning the color of the hydrogen out of ethanol. I think it's a blue one because we use all the CO2 to grow the sugarcane afterwards. So
okay, it's an interesting one politically whether you want it to be called blue, because blue has not all countries are fond of blue, right? Because of the CCS element to it. But obviously it's a BECS one if you do it with CCS, right? So yeah, interesting. I mean, blue is not in favor everywhere, right? So I think if you can get it called green, you'd be even better. But whether you can,
even better, yeah.
Yeah.
And the second point is there really a need to change the cars that are filled with ethanol with the internal combustion engine to batteries or whatever? I think such a hurry is not really needed for Brazil, maybe.
Well, it may not be. I think there's two questions, and I don't know the answer to them. One is, what's the overall carbon intensity of that chain? And I'm sure someone's worked it out, but I just don't know what it is. So it'd be interesting to compare that. Secondly, air quality. Again, I don't know, but you probably do, what the air quality is like of an ethanol combustion. But you're right to say that you're in a much better place here than everywhere else that is using diesel and gasoline and starting to try and go to ethanol blended gasoline. But that is not sufficient, right? Ethanol blending does not get you where you need to be. So you are in a better place. I think so perhaps the urgency here is different. But be interested to know what your end game is. And I think it's both about where you want to get to and how you're going to get there, no matter what country you're in. And a lot of the incremental improvements we make today are helpful but not sufficient. So there's steps in the right direction, but and I don't know the answer for Brazil, but it would be something to make certain that you've tried to answer.
Somebody else?
See, my challenge was you have to ask me a question.
I have one.
Yeah.
Concerning the Ceres Power fuel cell.
Yeah.
You mentioned that the operation temperature is around 500 degrees C. How is the start of this cell? For example, you burn some fuel to reach the temperature?
Yes. So yeah, the question is about how do you start up these high temperature devices? And you're right. You would, in all cases, you would burn some fuel to raise the temperature. It's a really important practical question: is startup and shutdown. How do you manage that thermally on the startup, and how do you manage it safely on the shutdown? Making certain all the fuel's purged and so on. But yes, I mean so you normally have to have some form of ignition system that would ignite some form of combustion, which would so you need some form of startup process and some form of startup components built into the system.
Great.
Yeah.
Renato?
So, Professor Nigel, thanks for your presentation. It's a very nice presentation. So my question is, what's the lifetime of the battery usually? These commercial,
Of the batteries or the fuel cells?
the
or
fuel
both?
cell, sorry, fuel cell,
Okay.
yes. And
Um,
the second question is, is possible recycling this fuel cell?
Okay, so both very good questions. Let's do the recycling one first. So I'd say that in electrochemical technology, the only electrochemical technology that's manufactured at a global scale today is the lithium-ion battery. There isn't another technology that's actually manufactured at scale. None of the ones I've spoken about are manufactured at scale yet. Even electrolyzers, not at the same scale. Lithium-ion battery recycling exists, but even that's still relatively nascent. Partly because, sadly, there is absolutely no commercial driver for doing it because it's cheaper to mine the material than to recycle it. So it's only regulation that makes you recycle. There is no economic incentive to do it with lithium-ion battery materials today. But obviously people are working hard to try and create lower cost recycling processes. So having said that's the situation for the only thing made at a world scale, you won't be surprised when I say that there isn't as yet really a recycling option developed for the Ceres fuel cells or indeed any solid oxide fuel cell. That doesn't mean it can't be done. It just means that it's following on behind. Now, am I concerned about that and do I see it as a big issue? The answer is no. The materials are, well, you've got metal, a lot of metal, so that's quite straightforward. And then you've got oxide ceramics, which are effectively not dissimilar to the sort of materials you mine. So you would go through some form of process, but that's got to be, it's for Ceres to say where they are with that, but it is, it's not something that's not being considered. But it's the same with all of the other solid oxide technologies. You would need to identify processes. I think the key at this stage for me is that you're ensuring that the design phase that you're locking technology into does not preclude a cost-effective recycling option. And I think that's where design comes in. So you want to make certain that you're making the technology as cost-effective as it can be to take apart. A lot of the cost is taking it apart, not only the chemical treatment. And this, your other question was around lifetime. So I have to say off the top of my head, I'm not quite certain what Ceres have said. What I can say is that the advantage of the metal support is that it thermally cycles hundreds and hundreds and hundreds of times rather than tens of times. And that it's been running in commercial trials of buses and so on very successfully. I know that Weichai did give a press announcement in February about its progress, which I can't remember, but go and look it up. But with some very encouraging numbers. So I think it's my personal view, and perhaps I'm biased, but it's the most durable solid oxide fuel cell solution. Whether it's sufficiently durable, well, time will tell, because really these things need to run for 5 to 10 years. That's what one wants. And they certainly run for years. I mean, we know, we've gone past the day where fuel cell lifetimes were measured in a few things. In my early days of solid oxide conferences, if you could get to 1,000 hours, you were doing well. Then people got to 10,000 hours and they were really pleased, and that was the main headline result of the conference. Now we are talking years. So, it's gone a long way, but it's still got, as always, you just want to continue to improve and get better. You'll know it works when Bosch release a product, because Bosch won't release anything that doesn't give you that sort of lifetime. So buy your Bosch fuel cell and see how it lasts when it's available.
Nelson?
Thanks, Professor, for the interesting lecture. I was wondering about in the same manner in Brazil, we're trying to develop electrolyzer from ethanol to produce hydrogen. Is there any opportunity to electrolyze natural gas, for example, based in efficiency to decrease the demand for natural gas, for example?
Okay, so you're saying getting hydrogen from natural gas, yeah. I mean, it's obviously that is how we make hydrogen today. We make it thermochemically, so it's an endothermic reaction. So we do that at a huge scale. That's how hydrogen is produced. So I think the answer is because it's already a fuel. So you can oxidize it, but you can't. You could electrochemically oxidize it, but you can't split it. So you can take it up to CO2 and water electrochemically. So as a fuel. And people are trying to do that, so-called direct methane fuel cells. I think there's less interest in those now because there's generally less interest in methane as a carrier, because methane has lots of other challenges around sustainability, cost, and its global warming potential, which is also very high, right? So it's a very potent global warming gas anyway. So people are trying to use less and less methane. I think that it's more on as a fuel rather than something you would split. Yeah, you could oxidize it, but I think there's less interest in that.
Okay. Do we have more questions? Yes.
First of all, thank you, Professor Brandon, for the rather enlightening presentation. I have a question regarding the vanadium flux cell. Actually, a two-part question. The first one would be, what is exactly the nature of the electrolyte used? Is like a ionic liquid or a coordinate compound? And the second is, what exactly would make a good electrolyte for such kind of cell? For instance, could we use niobium or other metal with high valence oxidation state to such aim?
Yeah. So I think if I got it right, the question is about the vanadium. Yeah. So this is a very acidic solution. So it's basically vanadium sulfate dissolved in sulfuric acid. You have to use quite high concentrations of sulfuric acid to get the vanadium solubility. It's about 1 molar solubility. Beyond that, the vanadium precipitates out. So, you've got a solubility issue. You'd like it to be more, obviously from an energy density perspective, the more metal salt you can get into solution, the better. In terms of what other things you can use, there is a lot of work going on alternative redox couples. And a number of things have been tried. So people are looking at aqueous systems and non-aqueous systems. So in aqueous systems, then you're governed by the stability of water in terms of the sort of maximum, if you're thinking of on the oxidizing side, you don't want to be water splitting. So you've got to think about what the maximum voltage is of your redox couple. It has to have obviously it has to be able to have a stable oxidized and reduced form. The advantage of vanadium, and the reason people have done so much work on it, is that you've got the same material on both sides of the membrane. So if you get any crossover, which you will, you're not creating a problem for yourself. So if you've got different liquids, completely different metal salts on both sides, you will get some contamination. So that's what people have struggled with a lot with other couples. The reason we've gone for a liquid gas couple, well, there are several reasons, but one of the benefits of that is if you do get a little bit of manganese crossover into the hydrogen side, it's a liquid in a gas, and you can just easily collect it and re-inject it. So that's not then doesn't become an issue. But yeah, you've got to have, you want something that's cheap, very important, because the cost of your energy storage solution depends on the cost of the electrolyte. So it has to be really as cheap as possible to have to be useful, right? So cost matters a lot. It's got to be sufficiently soluble that you can get a reasonable energy density. It's got to be electrochemically facile because you need to have it. It needs to be reversible. So you need a reversible redox couple because otherwise that lowers your round trip efficiency. So there are quite a few good review papers on options. Obviously, there are then organic systems and aqueous systems. There's quite a lot of work going on that as well. So, you know, I'm confident that there's more work that can be done, but quite a lot of work has been done trying to look at different couples. But, you know, that doesn't mean there can't be still innovation.
I see. If you are allowed one more question, in this case, from the manganese,
Yeah.
it's normal to have problem if the manganese oxide clogging the membrane?
Yeah, so you want to try and stop that manganese oxide forming, or if it does form, you want to stabilize it in a colloidal suspension. So what's written there is the problem. You don't want that to happen. So there are ways of stabilizing that reaction so that that doesn't happen. And I have to praise Anthony Kusinak and his team for finding the solution to that allowed that to become a viable option for us. We have explored a range of different couples. We've done vanadium hydrogen, we've done cerium hydrogen, and we've published work on those. But the manganese hydrogen, once you can stabilize it, is an attractive proposition because the manganese is so earth abundant and low cost.
Thank you very much.
I think there was a question at the back. Yeah.
Roberto?
I'd like to thank you, Professor, for is this working? Okay, I'm a bit far away from you, but I'm going to speak a bit louder. I'd like to thank you for the lecture. And I'm an undergrad student, so I have a question that is not directly related to the fuel cells, but it's related to something that might be a key part on the fuel cells. It's about hydrogen. I wouldn't say a lot, but many of my peers are not very interested on working with hydrogen because they are quite afraid. They say the hydrogen is surprisingly more, well, not surprisingly, more expensive than alternatives of other gas fuels, and it's, well, more dangerous because of the invisible flames and, well, highly volatile behavior. So how would you defend the use of hydrogen in a larger scale?
Sure. Well, look, very, very, very valid concerns to have, right? So let's talk about cost. And as I said, the cost of, it all depends what you're comparing it to, right? So if we're talking about green hydrogen, then the cost of that really depends on the price of renewable power. So if in places where renewable power is cheap, then green hydrogen will be cheaper. Or the feedstock, if you're making it from ethanol, obviously you need low-cost ethanol to get low-cost hydrogen. Some countries have got quite expensive alternative options, right? So natural gas, if you don't have, in the US, natural gas is cheap. They make lots of natural gas. In parts of Northern Europe, which don't have natural gas and have historically imported it from Russia, natural gas is not cheap anymore. And neither is it available. And if you're in Asia, which has to import almost all of its energy sources, it's never been cheap. So you've then got the comparison. So, you know, where does hydrogen sit in that space relative to those? Purely in cost. And there are parts of the world where hydrogen actually is cost effective today, but they're only where it's most advantaged. Of course, you've then got the carbon implications and the energy security implications. So what price do governments put on energy security? I think a higher price than they have historically. I think we got, you know, we were all in a world in which everything was tradable and you could buy everything from everyone. It was just a matter of price. We're now in a world where perhaps that's not, both with COVID and the shock of COVID and to world trade, and of course, Russia's invasion of Ukraine and the associated implications on boycotting Russian gas, certainly in Northern Europe. So it's not just about the price, it's also about the energy security. So that, and then it's about the carbon intensity, right? So there'll come a point at which even if natural gas is cheaper than hydrogen, should we continue to be using it in an unabated form? That's a kind of social question as much as it is anything else. So I think the price matters, but it's, for me, not the... ultimately, I think it will become a credible, if in places it already is, but it will become a more credible option in more places. The safety point is, of course, a very good one, and I haven't talked about it. All fuels are dangerous. Electricity is dangerous, methane is dangerous, gasoline is dangerous, and hydrogen is dangerous because they're highly exothermic, combustible, which is why they're a good fuel. Hydrogen has some unique challenges, and it has some unique... So if we're looking at hydrogen in a transport application, let's take that advantage, and we're comparing it to gasoline. Let's take that comparison. If you get a leak in a gasoline tank, the gasoline pools on the floor as a liquid, it vaporizes, and then it ignites, and you get a big fireball. If hydrogen leaks in an automotive crash, it's lighter than air, and it disperses. So it's actually safer. However, if you're indoors, then hydrogen is probably more hazardous, because hydrogen, if you were to leak hydrogen in here, it would gather in the roof void, and then it would see a spark, and then it would ignite. So if you're going to use hydrogen, you have to find a way of ventilating roof voids and so on. That's one thing. Fundamentally, we have to build hydrogen systems that don't leak, because it's unsafe if they leak. If we're going to put hydrogen into people's homes, and there are trials in the UK doing that at the moment, we clearly have to do it and not leak hydrogen, in the same way that we can't afford to leak carbon monoxide into people's homes because it kills them. We can't afford to leak hydrogen into people's homes because it's hazardous. So we have to find, there's no reason we can't have engineering solutions that deal with that, but there has to be proper regulation, there has to be proper training, you have to have proper parts, not just someone welding together two bits of copper pipe, but a proper fitting. So there has to be a process in place that can safely do so. You would need some form of sensor, like you do with the carbon monoxide sensor. At least in the UK, you have to have a carbon monoxide sensor next to a gas boiler burner. You'd have to have a hydrogen sensor. So there are controls, there are engineering controls you'd need to put in place. So it has hazard, but it doesn't have hazard that's not, it has hazard that's entirely controllable with appropriate engineering controls. But so, and so does everything else. So it's just different, but we can find ways of engineering safe solutions. And indeed, if you look at the Mirai and the Hyundai and the other fuel cell vehicles that have been driving around roads, it's been perfectly safe.
Thank you.
Okay. Thank you again, Professor Nigel. Let's so now thank the speaker again. We don't have any additional time.
Thank you. That's right.
So we are about to schedule the lecture speak for you.
Yeah. So I think I'm going to look at the ceramics
Yes.
stuff,
Yes,
and then
please.
lunch at 12:30 is fine, and then away for 2.
Yeah.
Yeah,